Final presentation on energy transfer via heat, we talk about phase change. So we learn pretty early on in our education that there are 3 different phases of matter: solid, liquids, and gases. And we also learn that we can transition between these different phases of matter. So if we have water, for example, in its solid phase as ice, the ice can melt and become water. And then, of course, we could take that water and we could boil it and we could turn that water into steam. So here are the different phase changes. And so, here's our solid. If we go from a solid to a liquid, it's considered melting. If we go from a liquid to a solid, it's freezing. If we go from a liquid to a gas, it's evaporation. And if we go from a gas to a liquid, it's condensation. And we actually can go directly from a solid to a gas, or from a gas to a solid. And these don't happen very frequently, and we usually don't talk about them much, but we have sublimation and deposition. So we're really not going to focus much on this one, but we are going to focus on transitioning from a solid to a liquid and a liquid to a gas, and of course vice versa. So let's start by looking at evaporation, and I know there's a lot on this picture, so I'm going to sort of talk a little bit about it. But evaporation is when you change from a liquid into the gas phase. And so what happens here is this is actually considered a cooling process. So if you think about, let's think about water, because water is an easy one to think about. Inside the water, there are water molecules. And those water molecules, they're at a certain temperature, and so they are moving around, right? They have kinetic energy. And that's part of having temperature, right? If something has temperature, that means the molecules have some average kinetic energy. So you have this material and these molecules have this kinetic energy. And so what happens is some of those molecules gain kinetic energy while others lose kinetic energy. So, they're bouncing around here, and you can even see them, right? Some of them are moving kind of slow, some of them are moving kind of fast. Molecules that are at the surface that gain enough kinetic energy can actually break free from the liquid. And that's what we're seeing here, is a couple of these molecules are just breaking free from that liquid. So the ones that are going to be able to break free from the liquid are the ones that have more kinetic energy, and they leave behind the molecules with less kinetic energy. So what happens is if the molecules that have more kinetic energy break free, then the average kinetic energy of the molecules that are left behind has gone down. And so that means that you're losing energy, right? So that's why it's considered a cooling process. I also wanted to point out specifically for water that water has a very high surface tension, so it's very hard for those molecules to actually break free. So this is a picture of a paper clip, and that paper clip is actually floating on the water, which a paper clip is made of it's made of a metal, and so in general it's more dense than water, so it should sink. But because of these surface effects, it actually can float if you're careful enough, and there's some things that you have to do to make that happen. But this is just showing that the molecules are really tightly bound together on the surface, so it's very hard for them to actually break free. So when they do break free, it has to be the ones that have a lot of kinetic energy here that break free, leaving behind that the less kinetic energy, the slower moving molecules that have less overall kinetic energy. So one example of this is when we sweat, our bodies actually produce liquid on the surface. That sweat evaporates, and our bodies are cooled down. So that's that process of. That's why it's considered a cooling process, is because we're losing those higher energetic gases, right? So another example would be boiling, and this is, I think, a little bit counterintuitive, but boiling is actually considered to be a cooling process, and it's exactly the same reasoning. So evaporation occurs over here. Evaporation can occur at any temperature. So you could just have a cup of water that you drink at night, right? And you leave it out and you don't go back to it for days and days, and the water level in that cup will go down because the water has evaporated. And so evaporation can actually occur at any temperature because those molecules just happen to break free. On the other hand, we can transition into a gas by boiling. So we can take liquid into its gas form by boiling the water. And so, and again, we're using water, but it doesn't have to be water. It can be any substance that's in liquid form. And what happens again is that molecules in the liquid can move into the gas phase. So this is a picture down here showing that this is a pot of water. It's on a stove, and it's hard to see, but there's like bubbles in here. And so what's happening is that the water is forming a gas inside the water. It's turning into its gas form. That's what those bubbles are. And then they're going to move to the top. And when they move to the top, they can actually break free. They have to actually be at a particular temperature, though, for these gas molecules to form. And they have to have enough pressure to remain in the gas phase to make it to the surface. So boiling doesn't occur at any temperature, right? It has to be the right process. So for water, water boils at standard temperature and pressure at 100 degrees Celsius. We have energy that's transferred in because the water is on a hot plate. So we've got energy entering, basically due to conduction. And then it's turning into its gas phase. Energy is leaving the water, leaving behind like the cooling. So we're putting energy in, we're letting energy go out because it's changing phase, and so that temperature is actually staying the same, right? So this is sort of like energy absorbed and energy emitted, right? It's absorbing energy because it's in contact, but it's also losing energy because of the water molecules turning into the gas phase. They are the higher energetic molecules, and they will transition. And so that's why it's considered a cooling process. Condensation is actually the opposite of evaporation. And so condensation occurs when the higher energetic molecules that are moving around actually are bouncing around, and some of them get caught on the surface. So like this one right here got caught on the surface. So they're moving fast up here, but they're the slower moving ones in the gas that get caught. And so this is considered a warming process because the liquid that's here becomes warmer. So the molecules that are in the gas phase are more energetic, they get caught, and the liquid actually warms up. So an example of this in terms of condensation that you've probably experienced is if you've ever taken some food after dinner and you're like, okay, well, we're going to save this for tomorrow. So you take some plastic wrap and you put it over the warm food, and then you stick it into the refrigerator. And what happens is that the water that was in the air that was trapped inside of the plastic wrap actually condenses, right? Because it has cooled down. The gas has cooled down. It has become less energetic, those water molecules, and they get caught into the liquid phase. So we could talk about the boiling point and the freezing point as well, but and what the boiling point might depend on. So it depends on the type of material that you have. So different materials are going to boil at different rates. We're going to focus a lot on water just because it's something that we use all the time. But water's boiling point at atmospheric pressure is 100 degrees Celsius. If I talked about some other material, like let's say honey, and I wanted to boil honey, right? It would have a different boiling temperature. We could ask the question, does water always boil at 100 degrees Celsius? And the answer to that is no. Water does not always boil at 100 degrees Celsius. It actually depends on the pressure of the liquid. So if you're at higher altitudes, water actually boils at a lower temperature. So it takes food longer to cook when you're at higher temperatures. So for example, if you are in Colorado and you are up in the mountains where you are at a higher altitude and the pressure is less, then the water will boil at a lower temperature. And so because it's boiling at a lower temperature, that's why it takes food longer to cook, because the food has to, it has to be heated to a certain amount to cook. And if you look at a pasta, if you cook pasta and you look at, the instructions for cooking the pasta, it'll tell you how long to cook the pasta, but then it'll also say to add time for so many altitudes, above sea level. On the other hand, you can have pressure cookers, and we can have water boil at a higher temperature. So if you can increase the pressure at the top of the fluid, you can actually have water boil at a higher temperature. And so this is an example for anybody that has parents or grandparents, or maybe you've done some canning before and used a pressure cooker. If you are going to can green beans, you actually have to use a pressure cooker because you need to make sure that you get all of the bacteria that could be produced from the green beans out. And the way to do that is you have to get it at a temperature that's higher than 100 degrees Celsius. And so you put your canned green beans in this pressure cooker, and it makes sure that everything will be good to eat at a later time. So when we talk about phase change, so we talked a little bit about phase change in terms of liquid to gas, gas to liquid. So we could also talk about solids to liquids. And so what's happening when you have a phase change from a solid to a liquid is that so the molecules are actually breaking apart. So when it's in its solid form, you've got basically the molecules are very bound together. And this is an example of a water molecule. And you've got these hydrogen bonds. And so as you add energy to the ice, those molecules, those molecular bonds basically break down, and then it becomes a liquid form so that the molecules are not so tightly bound together. And the opposite occurs if you have water and you want to freeze it. As the molecules slow down, right, so they're traveling faster, as they slow down and they get close, they start to form these bonds, and then they are in the solid phase. So higher energy moving towards a lower energy state. Right. So this is just another picture sort of similar to what we just saw there. So if you're going to try to melt an object or to freeze it, you can actually add impurities to water to make the freezing point decrease. And so obviously, if we're thinking about the freezing point of water, we know it's 0 degrees Celsius. But if you wanted to, you can add something like antifreeze, which will lower the freezing point of water because you're adding some impurities. So different substances will freeze at different temperatures, just like they will boil at different temperatures. The freezing point of water is also dependent on pressure, but it's even when you change the pressure, it's still very close to 0 degrees Celsius. So we sort of talked about this in the previous slide, but the molecules in the solid phase are bound together by the molecular forces, and as the molecules gain energy, they begin to vibrate, they move more rapidly, they break those bonds, and they move into the liquid phase. And then, of course, the reverse process is true for freezing. When you remove energy, they slow down, and then when they get close, they kind of bind back together again. One thing that's really important when we talk about energy and phase change is that when a substance actually changes phase, there is a transfer of heat that's occurring, but it always occurs at a given temperature. So when water changes phase from a liquid to a gas, and it's boiling, it boils at 100 degrees Celsius. And during that transition of changing from a liquid to a gas, it stays at 100 degrees Celsius. So at standard atmospheric pressure, substances change phase at a given temperature. So ice melts at 0 degrees Celsius and water boils at 100 degrees Celsius. And other materials will have different temperatures for boiling and freezing, or melting and boiling. But the big thing, and I have this underlined because it's really important, is that the temperature of a substance does not change during a phase change, even though heat is added or removed. So in the picture that I had of the boiling water, heat was being added to the boiling water, but in the process, the water molecules were turning into a gas, and so it was losing that same amount of energy, and the temperature of the water was staying at 100 degrees Celsius. So if we think about phase change and going from a solid to a liquid to a gas, if we want to go from a solid to a liquid, we have to absorb some energy. This solid would have to absorb energy to become a liquid. The liquid would have to absorb energy to become a gas. And then if we want to go in the other direction and we have a gas and we want to form a liquid, we have to release energy from the gas. And if we want to go from a liquid to a solid, we would have to release energy and then to go in the other direction. So we could ask the question, how much energy is actually required for a phase change to occur, and what's going to affect how much energy is required? So the first thing that's going to have an impact is the type of phase change. So there's a different amount of energy required to go from a solid to a liquid versus a liquid to a gas. This should kind of make sense because of the bonds that are formed that are having to break. So when you have a solid and you want to go to a liquid, you have to break those structures for it to go into the liquid form. And then from going from a liquid to a gas, you've got to have those molecules completely break free from the liquid, have to be high energetic, and they have to break free. So there's going to be different amounts of energy required depending on the type of phase change. It's also going to depend on the type of the substance that you have. Are you trying to melt an ice cube, or are you trying to melt a block of steel, or are you trying to melt a piece of plastic, right? Different amounts of energy would be required. Even if I had the same amount of each of these substances, it would require a different amount of energy, and they would occur at different temperatures. It also depends on the amount of the substance I have. So if I have a little tiny ice cube that I want to melt, or I have a huge massive block of ice and I want to melt it, it's going to require a different amount of energy for me to put in because I have a different amount of mass. And then finally, it's not directly dependent on temperature, but the substance changes phase at a specific temperature at atmospheric pressure. So the temperature doesn't actually change during the process, but in order for the phase change to occur, the object has to be at its temperature for melting or its temperature for boiling, right? I can't boil water at 50 degrees Celsius to turn it into a gas, right? I have to get it up to 100 degrees Celsius before that process can actually occur. So the energy transfer is not directly dependent on temperature, but in a way it is, because the substance has to be at its phase change temperature. So we have these two quantities called latent heat. We've got latent heat of fusion, and latent heat of fusion is basically going to tell us the amount of energy that's needed to change a substance from a solid to a liquid, and it's based on how much of that substance that we have. So the latent heat of fusion is going to tell us how much energy do I have to put in if I want to change a substance from a solid to a liquid per amount of mass that I have. So for example, water has a latent heat of fusion of about 334 joules per gram, or 334,000 joules per kilogram. So what this is saying is that if I have 1 gram of ice and I want to melt 1 gram of ice, it's going to require 334 joules in order to do that. And I guess I wrote that here. It requires 334 joules of energy for every gram of water to convert water to ice, or vice versa, or ice to water, right? It has to occur, though, at 0 degrees Celsius. So it's not directly dependent on that temperature, but indirectly you have to have the substance at its phase change temperature. I also wrote down the latent heat of fusion in terms of calories, because sometimes we use calories. So the latent heat of fusion for water is 80 calories per gram. If I have 1 gram of water and I want to convert it into ice, I would have to remove 80 calories of energy from that water in order to convert it into ice, or vice versa. I would have to add 80 calories of energy to 1 gram of ice to convert it into water. On the other hand, I have latent heat of vaporization, and the latent heat of vaporization tells us the amount of energy needed to change a substance from a liquid to a gas, or a gas to a liquid. And so in this particular case, we have, for water, the latent heat of vaporization is 2,256 joules per gram, or 2,256,000 joules per kilogram. So what does this mean? this means that if you have water, if you have 1 gram of water, and you want to convert that 1 gram of water completely into steam, it would require 2,256 joules of energy to convert that water into steam. Of course, it has to occur at 100 degrees Celsius, and so we have to have it at that temperature. So it requires more energy to convert water into steam, 1 gram of water into steam, so 2,256 joules. It takes more energy to convert that water into steam versus if I had ice and I wanted to convert it into water, it would only require 334 joules for 1 gram. So I've also given the answer in terms of calories per gram, just because sometimes we use calories. So here are some examples of latent heat of fusion for various substances. This is not necessarily something that we're going to use, but I just wanted to sort of give some ideas of how these are affected. So here's water right here, and the melting point of water is 0 degrees Celsius. Here's the amount of energy required to change from a solid to a liquid. Latent heat of fusion, this is joules per kilogram, so these are times 10 to the 5. And then here's water, boils at 100 degrees Celsius, and it requires 2.256 times 10 to the 6th, right? So these are the numbers that we had earlier. If we wanted to compare that to another substance, let's look at lead, right? Lead has a smaller latent heat of fusion compared to water, but it melts at a much higher temperature. So in order to melt the ice, it would require, the lead, it would require that the lead be at 327.3 degrees Celsius, but once it's at that temperature, it actually requires less energy to melt the lead than it does to melt the ice. And then I could go through that same process here, and if I wanted to take that liquid lead and convert it into steam, it would have to be at a super high temperature. And then I have the latent heat of fusion. This is the energy required to actually change it into a gas. So this just gives us a feel for how the latent heats are related to one another. Water in general, if you compare it, it's got a pretty high latent heat of fusion. It's hard for it to change phase. If you compare it to some of these other substances, it's one of the higher values. It's also pretty high in terms of other substances changing it into a vapor. So we could sum this all up, and we can say that one way that we can write down an equation that tells us how we would determine the amount of energy required to change phase is the energy that has to be added or removed depends on the mass of the substance and the latent heat that is required for that particular substance. So we're going to focus on water, so we would use here latent heat of fusion and latent heat of vaporization. But anytime something changes phase, the amount of energy required depends on how much of it we have and what the substance is and what type of phase change. That's the latent heat.